hear me is it's not there. All right, people, let me explain this again. So continuity, actually, I've just given the definition so far. We could be okay. Thank you to those of you who realized it was off. That was good for those of you that aren't here. So what's this look like? A continuous function. So let's draw this point A that we're interested in. And let's call that point right there A, comma, f of A. I need to get a different marker. This one's lost its edge. Here we go. A, comma, f of A. Much clearer. Now, do we know what f of A is? No, we don't. Does it make any difference? No, it doesn't. Does it need to be positive or negative? Makes no difference. So let me ask the question. Is f of x continuous? We just defined what continuous at a number means. At x equals A. Okay, talk to the person sitting next to you real quick. You should be looking for three things. Is f of x continuous at x equals A? Why?
Because f of A exists in the domain.
All right, volunteer, yes or no? Volunteer first, yes or no? Yes or no? Yes or no? Volunteer, Tana, perfect, yes or no? Tana, Jacob.
I'd say yes, it is continuous.
Why?
Because the function, so f of A exists.
Yep. Okay, real quick, how do you know that by looking at the graph? Yeah, there's a closed dot at f of A. At A, there's a closed dot, so there's an f of A. Keep going.
And the limit exists because the limit s is approaching from the left and s is approaching from the right equal the same length.
Good.
And then the limit of f of x is equal to the limit of f of A as x approaches.
That was perfect. Perfect. Why is it continuous? Just repeat what he just said. That was perfect. Now, here's my reverse question to you. What would cause it to not be continuous? Brainstorm with the people around you real quick. What are some things that it could look like that would cause it to not be continuous? That would cause it to not be continuous? All right, volunteers, what's some things that could make the limit not, or could make it not continuous? Andrew? Open dot, right. If there was an open dot right there, that would make it not exist, right? So thinking about holes, remember last time we were talking about holes, they made no difference to the limit. They do make a difference to continuity though, because if f of A is not equal to the limit as x approaches A of f of x, it is not continuous there. So a hole now is a big deal because it would make it not continuous. Guess what we call that, by the way? A discontinuity. There are types of discontinuities, but it's a discontinuity. What else would cause it to not be continuous? Joe, you had your hand up. What else? Limit doesn't exist. What are some things that could make the limit not exist? Sign, like the left and right hand limits, don't agree or don't exist, right? Either don't exist, they're going to like infinity or negative infinity or oscillating or something like that. What's something else that can make it not exist? Yep, Aaron. Piecewise function, right. They look like this. Yep. Limits don't agree. F of A would not be equal to both of them, obviously, because it's a function. It can't be both. What else? Holes. Okay, let's talk about that particular one, a hole. That's we talk a lot about that in pre-calc. We talk a lot about that in algebra 2. Like it's got to have something. That's called a removable discontinuity. Discontinuity. A removable discontinuity, what's that look like? And if you haven't found out, I really like to know what math looks like. A removable discontinuity. Sorry, I spelled it wrong the first time. I had to correct myself. What's that look like? Okay, so we got this beautiful, beautiful, beautiful function. Here it's got an open dot, and then we got this beautiful, beautiful, beautiful function. Okay, so let's call that A. And let's call this, I don't know, 7. So this point right here would be A comma 7. If we just made f of a equal to what, it would be continuous. If we just made f of a equal to what, it would be continuous. Yeah, so this we can simply make one value continuous. That's called a removable discontinuity. So let's give a rigorous definition. Show what it look like now. Let's give a rigorous definition. Let f be a function. F of x be a function that is continuous. That is continuous for every value except x equals a. So in other words, it's continuous for every point. So in other words, for every other point, f of c is defined, the limit of f of c exists, and the f of c is equal to its limit, except at this one point. Then, for every value except f equals a, then a is called a removable discontinuity. Continuity. How do we make it continuous? You just make it continuous by making it a piecewise function. So in other words, it's f of x when it's not equal to a, and then f of a is equal to, or at x equals a, it's equal to whatever number you need it to be equal to. I'll solidify that in just a second by doing an example of it. What are some things that can make it discontinuous? The whole, the limits don't exist, the limits don't agree, f of a isn't defined. So continuity is now taking the point plus the limit and putting them together. If they're equal to the same thing, then we have a continuous function. Or excuse me, we haven't said that yet. We're continuous at that point. Questions on that? All right, let's take a look at easy one or hard one. Let's take a look at an easy one first. Example number one. Let's look at f of x function. F of x is equal to, I don't know, 3x squared plus 7. Okay, so the question is, f of x continuous at x equals 4. Okay, now that's going to involve those rigorous definitions we gave over the last couple days. Is f of x continuous at x equals 4? Let's throw example 2 at you. Let's go for y is equal to, I don't know, what's easy one or hard one? Hard one. Let's go for a hard one. Let's go for let's do this. Let's go x squared plus no, need it minus. F of x is equal to x squared minus 9 over x plus 3 is, and I should call this g of x, by the way, because I already have an f in this problem. G of x continuous. What point am I going to ask about? X equals -3. Right on. Good job, guys. Okay, is it continuous at x equals -3? Now, I'm not even going to write this down. It's so sloppy. Ugh. The math teachers use this all the time. They say continuous means if you can draw the graph without lifting up your pen. That's like the least rigorous definition of math ever. In fact, I'm embarrassed it's on the internet. But some teachers will define it, and that's what it means, because it flows nicely. The limit's equal to the value. You can draw the graph without lifting it up. Yeah, if you can do that for all points, it's a continuous function. Every point is a point of continuity. So sloppy, I won't even write that down. But if that helps you understand, that helps you understand that it's sloppy definition. It's like going out. Like nobody knows what it means, but everybody has a basic understanding of it. Yes. Oh, of course. Yes. No problem.
Thank you.
I don't even know what that means. That's gibberish. Gibberish. All right, then let us, just a minute. Do you really need to do a lot of work for these? Not necessarily. This first one, is it continuous at that point? Yes, because why can you just take the limit directly? because it's a polynomial, right? We could just plug it in. And it turns out if we plug it in, that's going to give us the same thing as if we replace all the x's with 4. Yes. So is part A continuous? Yes. Is part B continuous? Why not? What does it fail? There's a hole at x equals aka f of -3 does not exist. Right. It doesn't exist. Now, could you make it continuous by just saying f of or at x equals -3 it's equal to something? Yes, you could. It's a removable discontinuity. Have a good day. I'll text that homework. Not quite finished with that section yet, but yet I feel we got more out of those 15 minutes than we would have if we sat around and didn't do anything.
So if you can't plug it in right away, then it's
Yeah, in fact, you can probably guess. All polynomials are what? Continuous at all points. It's those rationals, radicals that we run into trouble with.